Welcome to Study Loop.
In this problem, we have a constant electric field that we're told is equal to 4 times 10 to the 4th volts per meter. Okay? And we have a point charge in that electric field. I'll just put it there for now. And that point charge is 28 nanocoulombs, so 28 times 10 to the negative 9 coulombs. Now, I'm going to choose a coordinate system because we're going to need it later on, and I'm just going to pick the traditional coordinate system here, okay? And now we're asked to calculate the work for different displacements of this charge. So, if you remember, work is equal to the integral of force dot dl, and since we have an electric field here, that force is just replaced by Q times the electric field dotted with dl. Okay? So now our charge is a constant, our electric field is a constant, so we can pull out both of those constants and do this integral. So this is simply equal to, and as well I'm going to plug in what the dot product is equal to. So QE, and then with that dot product we get a cosine of the angle between the electric field and the displacement vector times the integral of dl, which is just the length that that vector moves. So I'm just going to call it L, since we have dl here already. So now, in each case, we just need to calculate this. So for part A, we're told that the particle moves 0.45 meters to the right. So this would be L vector is equal to 0.45 meters x hat. Okay? So now we can plug this in. Work A is equal to QE times 0.45 times cosine of the angle. And here, our displacement vector is pointing to the right. So therefore, the angle between this displacement vector and this electric field is simply 90 degrees. And if you remember, cosine of 90 is 0. So therefore, the work done by this displacement is 0 for part A. Now we're going to do something similar for part B. So in part B, we're told that it moves in a new direction. So my L vector is equal to 0.67 meters times y hat. Okay? So if we plug this in, work B is equal to 0.67 times QE times the angle, cosine of the angle between them. So our electric field is going up. Our displacement is in the y direction. So therefore it's cosine of 0, which is simply 1. So this cosine just goes to 1. And if we plug in our values for Q and E, we find that the work done by this is 7.5 times 10 to the negative 4 joules. Okay? And then for part C, we do the same thing. But this time L is pointing in two different directions, so it's going at an angle. So we're told that it's going downward at a 45-degree angle, and the magnitude is 0.67 meters again. Okay? So therefore, we can break this into components, and we find that sine of 45 is equal to y over 0.67. Cosine of 45 is equal to x over 0.67. And solving these, we have our components. So L is equal to 0.67 cosine of 45 x hat. And now, since it's going downward, we have minus 0.67 sine of 45 y hat. Okay? So now we have to actually do this dot product. So WC, or the work done during this displacement, is actually D dot QEY hat, okay? Which, as you remember, is simply LQE times cosine of the angle, but we have cosine of 45 here, okay? So what we can actually do is we just plug in these values, okay? So we get negative 0.67 times sine of 45, because only this y component will matter here, okay? Because if it's going at an angle, we only care about the component pointing in the direction of the electric field. So this actually works out to be sine times QE, okay? And when you plug in these values, you'll get negative 5.3 times 10 to the negative 4 joules. And that's it. That's your answer for part C.